Welcome to L'Hopital's rule and curve sketching. So recall, when it comes to sketching curves, limits are used to determine behavior. Near discontinuities. As well as to determine behavior or to determine end behavior. So since limits are involved, it may be that we need to use L'Hopital's rule. So we may need to use L'Hopital's rule to determine the behavior. So for example, let's consider the function f of x equals in the numerator 2 to the x minus 4. And in the denominator, x squared minus 4x plus 4. So first off, let's note that x squared minus 4x plus 4 equaling 0. X squared minus 4x plus 4 is x minus 2 squared. So this happens when x is equal to 2. So x equals 2 makes the denominator equal to 0. And so there will be a discontinuity at x equals 2. So I'm doing my discontinuities first. So let's go ahead and study the behavior near x equals 2. So we can look at both the left and right limits near x equals 2. So from the left, we can look at the limit as x approaches 2 from the left of 2 to the x minus 4 over x squared minus 4x plus 4. So if we plug in 2, this would be 4 minus 4 over 4 minus 8 plus 4, which is indeed a 0 over 0 situation. So we have our 0 over 0. So we will use L'Hopital's. So this becomes the limit as x approaches 2 from the left of, we would take the derivative of 2 to the x minus 4, divide by the derivative of x squared minus 4x plus 4. So we have the derivative of 2 to the x minus 4 in the numerator, derivative of x squared minus 4x plus 4 in the denominator. This becomes the limit as x approaches 2 from the left of the derivative of 2 to the x minus 4 is 2 to the x times the natural log of 2. So we have the natural log of 2 times 2 to the x up top. Derivative of x squared minus 4x plus 4. We are looking at 2x minus 4. This numerator will go to the natural log of 2 times 2 squared. The denominator goes to 0. So this is a case where we're going to infinity. Question is, will it be positive or negative infinity? Well, that numerator is positive. 2x minus 4 is approaching 2x minus 4 coming from the left will be negative. So we're approaching 0 from the left. So this should go to a negative infinity on the left. So coming from the left, we're going to negative infinity. From the right, we are looking at the limit as x approaches 2 from the positive side of 2 to the x minus 4 over x squared minus 4x plus 4. Once again, this is a 0 over 0 situation. 0 over 0, we can apply L'Hopital's rule. Once again, this limit will be equal to the limit as x approaches 2 from the right of, in the numerator, we would have the derivative of 2 to the x minus 4. In the denominator, we would have the derivative of x squared minus 4x plus 4. So taking the derivative of the numerator and the denominator, we get exactly what we were looking at before. We were just looking at the limit from the right this time as opposed to from the left. So we have a natural log of 2 times 2 to the x in our numerator. We have a 2x minus 4 in our denominator. So this will be a case, again, we go to the natural log of 2 times 2 squared in the numerator. This is a positive value. In the denominator, we will have, once again, go to 0. But as x approaches 2 from the right, we'll be looking at positive values. So in this case, we are looking at a positive infinity situation. So this is our end behavior. So essentially what we have at negative 2, coming from the left, we are going off to negative infinity. At negative 2, coming from the right, we are going off to positive infinity coming from the right. So this is our behavior at x equals negative 2. So that's our discontinuities and the behavior at the discontinuities. Next up, we want to look at end behavior. So for end behavior, again, we're going to do on the left and on the right. So on the left, we are looking at the limit as x approaches negative infinity of 2 to the x minus 4 over x squared minus 4x plus 4. I'm going to raise this actually so I can kind of fit things all in one go. 2 to the x minus 4, as x goes to negative infinity, 2 to the x goes to 0. So this top part is just going to go to minus 4. As x goes to negative infinity, x squared minus 4x plus 4 goes to positive infinity. And so on the left, our limit is just going to be 0. So what this means is on the left, we're going to 0, and we're going to 0 from the negative side, since we'll have a negative 4 over a positive number. So on the left, we're approaching the x-axis from below. On the right, we're looking at the limit as x approaches infinity, positive infinity, of 2 to the x minus 4 over x squared minus 4x plus 4. So going to the right, 2 to the x minus 4 blows up to positive infinity. X squared minus 4x plus 4 blows up to positive infinity. So here we have an infinity over infinity case. This means that we can use L'Hopital's rule. So this limit should be equal to the limit as x goes to infinity from the right, or it goes to positive infinity, of, in our numerator, we will have the derivative of the numerator, and then the derivative of the denominator down below. So we have up top the derivative of 2 to the x minus 4. Down below, we have the derivative of x squared minus 4x plus 4. So we are looking at the limit as x goes to positive infinity of the natural log of 2 times 2 to the x over 2x minus 4. Again, as x goes to positive infinity, natural log of 2 times 2 to the x blows up to positive infinity. 2x minus 4 also goes to positive infinity. So we have an infinity over infinity situation again. We will use L'Hopital's rule again. So from here, this is all equal to the limit as x approaches positive infinity of, we will again take the derivative of both the numerator and the denominator. So up top, we have the derivative of the natural log of 2 times 2 to the x. Down below, we have the derivative of 2x minus 4. This gives us the limit as x approaches positive infinity of, up top, we will have a natural log of 2 times a natural log of 2, or a natural log of 2 squared, times 2 to the x. And down below, we just have 2. Now this limit, the numerator, is going to go to a positive infinity. The denominator goes to a positive 2. And so in this case, we get positive infinity. So essentially this means that as x gets large, we're going off to positive infinity. Now concavity and that sort of thing, we will get from the remainder of our curve sketching techniques. So this is end behavior and discontinuity behavior. All used L'Hopital's rule. Now we can go ahead and combine this with all of our other information. So now let's combine with our other curve sketching techniques. So we have, first up, let's look at increasing, decreasing. So f of x was 2 to the x minus 4 over x squared minus 4x plus 4. So we have f prime of x should be equal to actually, I'm going to rewrite this so I can avoid the quotient rule. So this is 2 to the x minus 4 over x minus 2 in parentheses squared, otherwise written as 2 to the x minus 4 times x minus 2 to the negative 2. So the first derivative, f prime of x, we would do the derivative of 2 to the x minus 4 times x minus 2 raised to the negative 2. Then we would add to that 2 to the x minus 4 times the derivative of x minus 2 raised to the negative 2. So this becomes, we have a natural log of 2 times 2 to the x times x minus 2 to the negative 2. Then we have plus 2 to the x minus 4 times negative 2 times x minus 2 to the negative 3. And technically chain rule, we would have a times 1. So we are looking at essentially natural log of 2 times 2 to the x times x minus 2 minus 2 times 2 to the x minus 4 all over x minus 2 cubed if we wanted to rewrite that as one fraction with a common denominator. So this is undefined. So f prime of x is going to be undefined at x equals 2. I just realized these should have all been at positive 2's, at vertical asymptote I was sketching earlier. Sorry about the scrolling. Okay, so we're undefined at x equals 2. It equals 0 when natural log of 2 times 2 to the x times x minus 2 minus 2 times 2 to the x minus 4 is all equal to 0. This is one I'm just going to go ahead and use Desmos to locate where these zeros are. So if we plug this into Desmos, we had the natural log of 2 natural log of 2 times 2 to the x times x minus 2. And then we had minus 2 times 2 to the x minus 4. So it looks like I've got 2 zeros, one on each side of 2. Oh, nope, I have an undefined at 2. And then I have a 0 at about 4.299. So technically this equals 0 at 2 and at 4.299 approximately. So here we have x equals 0 or 4.299. This x equals 0, we're going to cross off, since f prime of 0 is undefined. So we have critical values at 0, at 2. That should not be 0. Sorry, that should have been at 2. I apologize. F prime of 2 is undefined. X equals 2 gave us a derivative of 0. So we have 2 critical values, namely at 2 and at 4.299. We know that f prime is undefined at 2. We also know that f is undefined at 2. F prime is 0 at about 4.299. Then we need to figure out the signs in between. Let's go back to our graph and add in our derivative. So let's go ahead and divide by x minus 2 cubed. So that's the entire derivative. And here's our graph. So let's take this and put it into the notes. So this is our graph of f prime. We have that f prime is negative before 2 and between 2 and 4. It switches to positive after 4.299. So we know that f is decreasing on till its asymptote. We know it's decreasing again after the asymptote, switches to increasing at 4.299. So we have a relative minimum at about x equals 4.299. Now let's look at, so that's our increasing, decreasing. Now let's look at concavity. So f prime of x was natural log of 2 times 2 to the x times x minus 2 to the negative 2. Then we had minus 2 times 2 to the x minus 4 times x minus 2 to the negative 3. So the second derivative, we would be looking at a natural log of 2 squared When we take the derivative of 2 to the x, we get another natural log of 2 times 2 to the x. Actually, let's write out the rules. So we'll have a derivative of natural log of 2 times 2 to the x. Multiply that by x minus 2 to the negative 2. Then we would add to that the natural log of 2 times 2 to the x. Multiply that by the derivative of x minus 2 to the negative 2. This is running the product rule on that first part of the first derivative. Then to that, we will run the product rule on the next part. So to that, we will add the derivative of negative 2 times 2 to the x minus 4. And then plus a negative 2 minus 2. Let's do this. Sorry, I have to first multiply. I have too many things going. Okay, so that's the derivative of the first. We would then have to multiply by x minus 2 to the negative 3rd. Then we would have plus negative 2 times 2 to the x minus 4. And multiply that by the derivative of x minus 2 cubed. So I've done 2 product rules here, one on the first piece and one on the second piece. So the derivative of x minus 2 to the negative 3 is that last derivative. So we are looking at a natural log of 2 squared times 2 to the x times x minus 2 to the negative 2. Then we would have minus 3 times the natural log of 2. Sorry, minus 2 times the natural log of 2. Times 2 to the x times x minus 2 to the negative 3rd. That's power rule on that x minus 2 to the negative 2. Technically, we would have a times 1 from the chain rule. Then we would have a minus 2 times the natural log of 2 times 2 to the x times x minus 2 to the negative 3rd. Derivative of negative 2 times 2 to the x minus 4 is negative 2 times natural log of 2 times 2 to the x. And then we have, for the last row, we would have a minus 2 times a negative 3 would become plus 6 times 2 to the x minus 4 times x minus 2 now to the negative 4th after we apply the power rule on that x minus 2 to the negative 3rd. Again, this is the natural log of 2 squared times 2 to the x times x minus 2 to the negative 2. We have 2 of these minus 2 natural log 2 to the x times x minus 2 to the negative 3rd. So this becomes minus 4 times the natural log of 2 times 2 to the x times x minus 2 to the negative 3rd. And then we have plus 6 times 2 to the x minus 4 times x minus 2 to the negative 4. So let's go ahead and again put that in decimals. So we are looking at the natural log of 2 squared times 2 to the x times x minus 2 raised to the negative 2. Then from that, we were subtracting 4 copies of the natural log of 2 times 2 raised to the x times x minus 2 raised to the negative third. And then we were adding on 6 copies of 2 raised to the x minus 4 times x minus 2 raised to the negative 4. So we're now looking at the purple function. And it looks to me like this is undefined at x equals 2, and then it's nowhere else 0. Right? So it looks like, based off this graph, that we're undefined at x equals 2. And nowhere else 0. So let's add in this picture. But again, this is the second derivative. We have that's undefined at x equals 2, and it's nowhere equal to 0. Now, obviously, if we have a graphing tool, we might as well just graph f. It seems kind of silly to use the graphing tool for the first and second derivative and not use it for the original function. I just don't want to spend the time trying to solve this algebra here. So in any case, our second derivative is of little, has not a lot going on. Our second derivative is undefined at 2. We also have that f was undefined at 2. That does not always have to be the case. Our second derivative is negative to the left of 2, positive to the right of 2. So we start off concave down, switch to concave up. So we can now put all this together. So putting all this together, our primary point of interest is at x equals 2. At x equals 2, we know that we have a vertical asymptote. We also know that we have a horizontal asymptote going to the left at x equals 0. We know that we are concave down. So anything over here, we're concave down. So this whole piece is concave down and decreasing. So we can essentially just do a horizontal asymptote below the x-axis, followed by a vertical asymptote going to negative infinity in that part to the left of 2. Our next point of interest is at about 4.399. Our next point of interest was a relative minimum. We don't know the y value for that. We can plug it in to find out. So at the relative min, f of 4.399, or was it 299? 299. So f of 4.299 we would be looking at 2 to the x minus 4 over x minus 2 squared would be a positive value over a positive value. That's all we really need to know. So we know we have a positive relative minimum. We're starting with a vertical asymptote coming down from x equals 2 from positive infinity. We know that we are concave up for this part. We decrease until our relative min at 4.299. And we increase beyond that. We are concave up for this entire component. So we know our next piece until that 4.299, we knew that it was decreasing and concave up. Oops. And then to the right of our 4.299, we knew that we were concave up and increasing. So this again is a rough sketch. Obviously, this problem was not particularly pleasant for solving for where our functions derivatives were equal to 0. And I used graphing tools to do this, which kind of defeats the purpose of curve sketching without a graphing tool. But you can kind of see the idea of how we can use limits to figure out what's going on the ends, and then use our other techniques to figure out increasing, decreasing, concavity, etc.